In this lesson, we're going to be looking at 2D vectors, and you might recall that the way that I explain this is that if one-dimensional is like a train track that you can only move forwards and backwards on, two-dimensional is more like a floor because you can move forwards, backwards, left and right, any directions you need to. So, as we get into this 2D stuff, there are a few details that we need to be careful about. First of all, a 2D vector diagram that we're drawing is non-collinear. That's important because in the last lesson, when we did collinear diagrams, where everything was one-dimensional, we could just add things together directly, pretty much like 5 plus 3 equals 8. It was because, like, everything was on the x-axis. It might be that we had to subtract some things. It might be that we even had some negative vectors, but that's okay. It was still just like straightforward adding or subtracting of them almost. But because we're doing these non-collinear diagrams, stuff that we're going to see has an x and a y-axis, it means that we're going to be drawing a lot of triangles, and it's mostly going to be right-angle triangles. And we'll even see as we get into some of the deeper, more complicated stuff, even if it would be better drawn as a non-right-angle triangle, we can draw multiple diagrams and still make it a right angle. So that means that you do have to be familiar with SOHCAHTOA and Pythagoras. If this is something that you kind of struggle with, there is a worksheet that is on the Google Classroom that you should really be looking at, because you do want to make sure that you've practiced this enough for just kind of straightforward, here's a triangle questions, instead of struggling with it when we're also piling physics on top of it, which is not what we're going to be doing at first. We are going to be pretty much just dealing with let's get the triangles done, but it will come to a point where you have to be doing the physics as well at the same time. When you are doing these problems then, what you kind of have to do is use physics to set up the diagram. And by that I mean follow the rules from the 1D stuff, like vectors have to touch head to tail. You can pick them up and move them as long as you don't change their size or direction, all that stuff. We use the physics to set up the diagram, making sure that our diagram is vectors. They have to have arrowheads, okay? Because we have to be able to follow the rules of like head to tail. Then you switch to math and you do it like any other trig problem, because you're going to have a big triangle and you'll use Pythagoras or SOHCAHTOA or whatever it is that lets you solve the answer. And then usually we kind of half flip back to physics so that we can take whatever we've been doing and come up with a final answer, a statement that we can make. Now, probably one of the most important things to remember, though, is make sure your calculator is in degree mode. If you're on a TI Inspire, that's pretty easy because you can just look up in the top right-hand corner and next to the gear icon, it should say DEG. If you're on a TI-8384, you will have to go into the mode settings and check in there. It's a few steps down. But on TI-8384s, if you reset the calculator, it automatically jumps back into RAD mode. So you want to make sure that you're checking that before starting any of these questions. Now, we're going to use something called components of vectors, and this is going to mostly look like, hey, we're drawing right-angle triangles to you. The components are the individual parts that will add up on the x and y axis to give us our overall resultant. Best way to see this is to actually look at a kind of a simplified question and draw the diagram from it, and then we can use those names while we're looking at it. So I ask you to drive or to look at the example of driving a car 10 kilometers east and then turning a corner or whatever and driving another 7 kilometers north. And I ask you to determine the displacement. Now, this is where it's a good idea to pause this video and just take a moment and try to draw just a simple vector diagram of this. Try to draw the pathway that Pac-Man would follow to show that he first went 10 kilometers east and then went 7 kilometers north. And then draw what you think the displacement would look like on that. Okay, so if you've got your own diagram now, we'd be looking at, first of all, showing that we move 10 kilometers east, and so I've drawn a vector that points to the right because that's usually what we interpret as being east. I don't even have to write the E in square brackets on the diagram because the vector itself shows that it's pointing east, but I'm doing it here just to make sure that you understand I'm trying to show the vector that points east. Then I add my second vector touching head to tail of the part driving 7 kilometers north. And notice a few things. First of all, this should look almost like we're looking at some route on Google Maps. We're floating in the air looking down on this, and we see the route being drawn out first east and then north. And it really does need to look like that idea of, Pac-Man following the arrows. There's only one pathway that he can follow on here, chomp, 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 to be able to get from the start to the end. Another thing to consider is in this diagram, besides me doing my best to show the vectors pointing the actual directions they should point, is I tried to make sure that the 7 kilometer vector is noticeably shorter than the 10 kilometer vector. Remember, I'm not measuring this exactly with a ruler necessarily. I just got to make sure that it's easy to see that it's shorter. Now, the question to ask, I should mention this. These are the components. These are the individual parts that added together, adding head to tail, will give us our resultant. Now remember where a resultant goes. A resultant is drawn so that it touches tail to tail, head to head, from the start to the finish on our diagram. Sorry, I forgot that little note there. So there's my resultant. Tail to tail, head to head. And that resultant is showing us that if instead of following that path east and then path north, if, as long as there wasn't things in the way, I was able to go kind of diagonally across there, I would actually start and finish at the same spot. And that's the idea of a resultant, is it has to show us the same result as the vectors that we're adding together. Now, if I asked you for the resultant, which by the way is the displacement because it shows start to finish, where we started, where we ended, the easy part is to grab Pythagoras and do a quick little calculation for that. And something I'm often asked is, do I have to show this work? Yes. Sometimes people will tell me, but it's only Pythagoras. It doesn't matter. In physics, we have to show formula, substitution, answer with sig digs and units for everything that we do. So that's what I've shown here. I showed my formula, I showed my substitution, I solved for it, and I did round off for sig digs. The 7 kilometers being 7.0 limits me to only 2 sig digs. And because I was doing squaring, that's basically multiplication. So that's the rule that I'm following, least number of sig digs. Now the part that gets a little bit kind of iffy is, what am I going to say about the direction? Because I can't just say something generic like northeast. If I say that in physics, it means that it's exactly 45 degrees between north and east, and this isn't. But I am going to be looking for this angle right in here. That's going to be the angle that I need. So I need to not only be able to calculate how big it is, but I also need to be able to show something about what that angle means to give an answer that's meaningful all the time. And that's where we get into the rules. Oh, it's not letting me click over here again. That's where we get into the rules for how to do directions in our answers, how to state them properly. So, I'm not saying that the previous one is 35 degrees, but let's say it was 35 degrees. If I just said 35 degrees, people could legitimately ask me 35 degrees pointing where? I have to be able to say something more than just the angle so they know where that 35 degrees is. There are two systems that are accepted, and one of them is actually split up into kind of an older and a newer version of it. And you're expected to know all of them. Okay, you have to be able to not only give your answers, but also read directions given to you in any of these systems, any way that we kind of mix them together. So the first method is known as the Cartesian method, and that name should be familiar to you from math. That's the one that I think a lot of people, to at least some extent, feel more comfortable with, even though there's some stuff that we do with it that usually means we have to do a bit more stuff with it if we're going to do calculations later. The second method is called the navigator method, and you probably saw at least a little bit of this in Science 10, but unfortunately the way it's shown in Science 10 often involves it being kind of jumbled around and not exactly the way it should be. The Cartesian system is based on this classic idea of making the positive x-axis 0, and then, kind of important to us here, is the idea that we are going counterclockwise around this like big unit circle sort of thing. So that 0 is on the x-axis, positive x-axis. 90 degrees is pointing straight up. It's basically the positive y-axis. Going further around until we get to the negative x-axis is 180. Negative y-axis is 270, and as we get back all the way around to where we started, technically you could call it 360 degrees, but we'd basically go up to 359.999999 sort of thing, and as soon as we get back to the beginning, we would call it 0. Now, the advantage to this system is that we are using it in math, which is great. The disadvantage is it's basically arbitrary. And what I mean by that is, what if in the middle of a test you forget that it's the positive x-axis that's 0, and you make the positive y-axis 0? Or what if instead of going counterclockwise, you start going clockwise? You get totally different directions, and that would kind of screw us up. It means that you'd be either interpreting it wrong or getting the wrong answers, giving the wrong answers yourself from it. So we got to be kind of mindful of that. Now the other system, and don't worry, I am going to give examples where we practice doing everything with all of the systems once I've spoken a little bit about both of them, is the navigator method. And this is the preferred method. Your textbook doesn't use it necessarily as much, but it's now considered to be the preferred method a lot of the time. And it's because it's based on northeast, west, south, the main compass points. And because of that, it's not arbitrary. You can basically go anywhere in the world looking at any map that just about anybody uses, and even though they might translate it into their own language, these are the compass directions that everybody has agreed on. Now, the disadvantage is that you have to be careful with how it's written. That's the biggest problem that we've got, because there are, like I said, two different styles to the navigator method. This is the one that's split into the old way and the new way. It does mean also that because we can be doing angles from various compass points, and you'll see what I mean about this in a moment, that you can even have two different number values for the angles, and that can even make it a little bit weirder. So, going into this example, I've drawn a vector, and usually we don't draw the whole sort of like Cartesian plane, northeast, west, south, but I want to draw the whole thing so that you can kind of see it as a reference for this vector. I've got this vector that's pointing kind of northeastish at a 30-degree angle, measured from where north is. And I want to know what this direction is. So if I am doing this within the Cartesian system, what I've got to consider is that this is my 0. This is, whoops, sorry, I did that wrong. I did not mean to write 180. That's my bad. I meant to write 90. And this is 90 degrees. So if I am hitting things and making things appear that shouldn't, I've got to recall that this would mean that I am 30 degrees sort of shy of 90 degrees. That means that this angle right here, if you want to think of it that way, is 60 degrees, because 60 plus 30 is 90 degrees. Because of that, because the Cartesian system always starts at this 0 point on east, that means that this angle, the 60 degrees, is what I actually have to state. So if I was doing this in the Cartesian system, I would actually be giving my direction, with it not letting me click anymore, as just 60 degrees. I wouldn't say anything else about it. That might seem kind of simplified or too easy or something like that. But honestly, this is just the way the Cartesian system works. So you're not necessarily giving the angle that's written in the problem. You're doing it based on where the Cartesian system puts the angles. Now, if instead I am using the navigator system, I don't know why that keeps on jumping up. The easiest way to write it is north 30 degrees east. And that's because what I'm basically doing in this system is I'm using north as a reference line because I measured the 30-degree angle from this north vector. So that means that I can put down north as my reference line. 30 degrees, it's kind of like we're leaning over to the right. We're going towards where east is, even though we never get there. So north as a reference line, 30 degrees towards where east is. North, 30 degrees east. And we have to put that whole thing inside the square brackets. You can't put just like the angle in the brackets for this one, because otherwise the north could look like newtons, for example, or something like that. So it's north 30 degrees east. But remember, we also know that this angle over here must be 60 degrees because 60 plus 30 is 90. We'd refer to that as a complementary angle because it complements the 30 to add up to the total 90 that has to be in that quadrant. So if that's the way I'm going to say it, I would be using east as a reference line because I'd be measuring this angle in here as 60 degrees. So east is now my reference line, 60 degrees, and I'm kind of leaning up towards, even though we don't quite ever get there, towards north. So east, 60 degrees north. Both of those written that way could be considered correct, and both of them are part of what we usually refer to as the new navigator system. But that does mean that there's an old or classic navigator system, and this one kind of sounds weird when you say it, but I'm going to give you a way to kind of help you with it, hopefully. So, in the old school navigator system, you would say something like 30 degrees east of north. Basically, notice that that means I'm taking this first answer I've got and I'm writing it by basically almost taking like this north and throwing it to the end, 30 degrees east of north. Now, a way that I used to say this when I was a student, when I was looking at this angle up here, is we can't write it this way, but it's the way I said it in my head. Instead of saying the word of, I said the word from. So I would say 30 degrees east from north. So right in here, I am 30 degrees going towards east, east, from a starting point of north. So 30 degrees east of north. Now, if that's true, then using the complementary angle, I would have been going 60 degrees towards where north is, starting from east. So 60 degrees north of east. So this can be a lot to look at, I know. And this can be a lot of stuff to kind of say, wow, I got to be able to do all of these. Here's a couple of things to consider. You, when you're giving a direction, only have to give one of them. You're not, in fact, it's considered wrong to give multiples of them, unless you're specifically asked to give multiples of them. You're supposed to just do one method when you're giving the answer. So I would say for you giving answers, try to focus on the method that makes the most sense to you and just go with it. At the same time, you do have to be able to read any of these methods, because I can give you this vector written as any of those, and you'd have to be able to interpret it to figure out what it means, to be able to draw it on a diagram. So pause the video at this point and try to do this one. See what you can do. And try to do it as all 5 methods. Okay, so let's talk about a few things here. If I was doing the Cartesian method, 0 to 90 to 180 to 270, notice I'm 40 degrees shy of being at 270. That means that in the Cartesian system, I would be giving this one, showing all of them now, as 230 degrees, because this angle would be 230 degrees. If I was going to use the navigator system, and I was using this space right in here with the 40 degrees, I'm south 40 degrees west, because I'd be using south as my reference line, and I'm going 40 degrees towards west. I could also do that in the old navigator system as measuring from here still 40 degrees west of south. 40 degrees going towards the west, starting from south. 40 degrees west of south. I also have my complementary angle, 50 degrees, because 50 plus 40 is 90. So if this is my complementary angle, I could give the direction as west 50 degrees south, because I'm using west as a reference line to measure this angle. So west 50 degrees going towards south, west 50 degrees south, or 50 degrees south of west. All of those answers are correct. All of them say the same direction. So, going back to the question that we had at the very start of things. Here's that diagram. We already had figured out what the side was. We know that it's 12 kilometers, but we need to give the direction. And we always, unless we have a very good reason to do otherwise, we always measure the angle where these two tails meet, where the tail of one of my components touches the tail of my resultant. So if I'm going to figure out that angle, I want to actually do it with the 7 and the 10 sides. I don't want to use the 12 if I don't have to, because the resultant is something I calculated, and if I calculated it wrong, then even this calculation is going to be wrong. But I can use this side, because it's the opposite side from my angle, along with this side, because it's the adjacent side, to be able to calculate my angle. So I'm going to use tan, opposite over adjacent. 7 is the opposite, 10 is the adjacent. So I'll type in 7 divided by 10 on my calculator, but then don't forget you have to inverse tan that, because I don't want the tangent of the angle, I want the angle. So you inverse tan, and as long as you're in degree mode on your calculator, you should come out with a final answer that rounds off to 35 degrees. And once again, I have to emphasize, this is a calculation. We are doing it in physics class. I am required to show a formula, substitution, final answer with sig digs, and the degrees, that's my units. So I'm still following all the rules. I should give this though now as a final answer. This vector is east, and that's what I'm using as a reference line for my angle. So I would be east 35 degrees, going up towards here where north is, even though I never quite get to it. So best way to probably write this as a full answer is 12 kilometers, and then in squared off brackets, east 35 degrees north. Now, if somebody else was doing this question and they were doing it with a complementary angle, they would have 55 degrees, because 35 plus 55 equals 90. And then they might have answers like north 55 degrees east, and that would still be correct. Just a couple of questions for homework, even though we've done a bunch of stuff here, because the textbook basically assumes that you'll have done a bunch of other stuff with vector diagrams before doing a lot of stuff with directions. But remember, check out the worksheets that I do have in the Google Classroom as well.